Alright, so here's where I left off on part 1 of the video with Lewis acids and bases. Now, when you start talking about accepting and receiving pairs of, or accepting or donating pairs of electrons, then you should start thinking about bonding. So we had a definition that started with what does it have in the formula, and then we expanded our acid-base definition to Bronsted-Lowry, which is how does it transfer hydrogen, which not all compounds have. Not all compounds have hydrogen, though a lot do. And now we've expanded the definition further, because all of the other things, if we went back and analyzed them, that are acids and bases under the other definitions, would also fall as acids and bases under this definition. We've expanded beyond to electrons, and all molecules, all atoms have electrons. So the Lewis acid and base definition could be expanded and applied to very many things. But it has to be an electron pair, not just one, electron being transferred or something like that. So let's take a look at an example. Alright, so we're going to take a look at the example of BF3 and NH3. And this is a really clear-cut way to see the Lewis acid and base definition at work. So let's get all the molecules up here. So here's the BF3. This is the structure for it. See the boron with a single bond to 3 fluorines. And boron's geometry, Lewis structure allows it to be stable with a small violation to the octet rule, because there just aren't enough electrons present here for boron to have a lone pair to satisfy the octet rule. But you could kind of think of it as, it sort of wants to have another pair of electrons there. And then here's ammonia with this lone pair of electrons just sticking out there. Yep, it's there. And so what these will do, if you combine them with each other, is they will bond and form a single bond between the nitrogen and the boron. And so what happened here is the Lewis definition of acids and bases. So the base was the electron pair donor. NH3, in other words, gave a pair of electrons to the boron, and then the boron trifluoride was the receptor, or the acceptor of those electrons, so that made it an acid. Alright, we won't use this definition very often, but it's there. So if you ever take organic chemistry, it'll be even more important. Alright, here is a summary of the properties of acids, not the properties, the theories of acids and bases. And also here's a graphic just to show you that Arrhenius defines a small number of things as acids and bases. Bronsted-Lowry broadens it, and Lewis broadens it even more. And another thing for you to think of is that all acids that are Arrhenius acids will also be Bronsted-Lowry and Lewis acids, while and that also, so Bronsted-Lowry, all of those would also be Lewis acids and bases. But there are some that like the Lewis acids and bases, some of them might not be Bronsted-Lowry, and the same would apply. Some Bronsted-Lowry acids and bases might not be Arrhenius acids and bases. Alright, so let's talk about the strength of acids and bases for just a moment. So strong acids ionize completely in solution, and that's similar to the term dissociate, but since this is a covalent compound, we only use the term dissociate for bases, so just kind of keep that in mind. You might see the term ionize there for an acid breaking into ions in solution. And that happens to a large extent, so there would be very little HCl left together, and most of the HCl would be separated into ions in solution. Whereas a weak acid, like acetic acid, that's vinegar, it might mostly stay together with the hydrogen attached to the acetate, and probably less than 5% of it would actually separate into hydrogen ions and acetate ions. Alright, so strong and weak are kind of qualitative terms. There's not a numerical value to them, but we will come up with a quantitative description for those and use that extensively in AP Chemistry. Alright, so strong bases dissociate. They are ionic compounds. They dissociate completely into metal ions and hydroxide ions in aqueous solution. That means when you dissolve them in water. So like when you drop some sodium hydroxide into solution, the sodium and the hydroxide ions separate completely. Weak bases, on the other hand, don't completely dissociate in solution. For example, the ammonium hydroxide, when you put it in solution, it forms some NH4 and some OH-, but most of it stays together as NH4OH. Alright, here's a list of the strong acids. There are 7 of them. If we were taking an exam, I would recommend that you memorize those, or AP Chemistry students in the future I'll remind you of those, and you will have to memorize those. Alright, so the strong bases. If you want to get in a fight with a chemist, start talking about which bases are strong. We'll agree everything in group 1 is a strong base, and then the ones that dissolve well in group 2 are the calcium through radium, the heavy ones. And there's some people that will say calcium hydroxide is a strong base, and some people will say it doesn't dissolve very well. But to the best of my ability to identify these, calcium through radium hydroxide, as well as all the group 1, so like sodium, potassium, lithium hydroxides, those are all considered strong bases. And then it's like, well, what about the weak base? If it's not on the list here, it's weak, and that's easy enough. So you have to memorize which ones are strong, and then the weak ones are the ones that aren't strong. Okay, I'll briefly mention this acid dissociation constant, and basically say that gives you a way to quantify, for example, for an acid, how much H plus and how much X minus is actually in the solution for the acid. So you can imagine that for a strong acid, there will be a lot of the H plus and the X minus from the acid, and not a lot of the acid, so you get a big number for Ka. Versus a weak acid, there would be small numbers for the H plus and the X minus, and a larger number for the non-ionized acid. So you would get a small number for Ka. So basically, if the Ka value for an acid is large, then you have a strong acid, and if the Ka value is small, then you have a weak acid. Alright, and that will conclude this section, and we'll pick up in the next section with how to calculate pH and pOH. Thanks for watching.